Okay, so let's go ahead and get started. We're going to work on chapter 10 and 12 a little bit today. So hopefully you have some writing utensils and that sort of thing. So a little bit of background about chapter 10. Probability theory, we kind of know about probability theory already. Numbers need to be between 0 and 1, and nothing that can exceed 1. So again, just a few comments. So let's see here. So probability theory is like our bridge between data collection and inference. So all this sampling work, all this about sampling 500 students and getting information about a population, probability theory helps us with that. And we had an example about global warming's impact on the weather from about 2 years ago, and we only sampled 1,009 people, and we got some data. So if we were to go ahead and sample another 1,000 people, we probably get slightly different results just due to variation. But probability theory helps us understand maybe the randomness that goes with certain variations. So let's see here. There's this whole chance behavior concept, but things pretty much behave the way they're supposed to in the long run. So I have a little activity for you, all right? So what you're supposed to do now is go ahead and, let's say, take your row, and let's say if you're in the center, take your whole row. If you're on the edges here, maybe take like about 5 rows. So let's say like this 5 rows here, very comfy, nice. You 5 down here, and then up top here. So kind of go half and half. But if you're in the center, take the whole row. And what I want you to do is jot down the number of women in your row and the number of men in your row. Okay? Now, it could be a very quick answer for some of you because no one's here. Midterm was yesterday. And then the proportion of women in that group. So I will be an honorary member of the Crow's Nest for today's class. So if I'm in the Crow's Nest, there's how many women? 1, 2, 3, 4, 5. 5 women. And if I'm an honorary member, and Jeff will put you in there as well. So that's 1, 2, 3 guys. Yeah, 3 guys. And in our case, we had 8 students. What percent were women in my group? Or what? Give me the fraction. How about that? What's that fraction? 5/8, right? Which is about 7.625, I think. Yeah, I'm not going to do that. Okay, so that's going to be 5/8, 0.625. Now, theoretically, if I were to kind of take the data from the entire class, theoretically, the more students I sample, the closer this number should get to the true percentage, which should be in the neighborhood of 50%. So if you start out with this group here, it was 1, 2, 3, about 5 women, all 5 women, right? But as they included more and more people, it should become lower percentage of women, higher percentage of men. So probability theory tells us that in the long run, things behave the way they're supposed to. So let's say Dr. Baker's shooting free throws. All right, I'm typically about an 80% free throw shooter. That's like in my backyard. But in the game, I'm probably like 70%. Those like old man leagues, 30 and over type thing. Okay, so I might make 4 in a row. But over time, I'm going to probably converge back to my 70%. Okay, I might miss 4 in a row, but over time, I'm going to converge probably back to my 70%. So that's what probability theory kind of helps us with. All right, so we have more definitions and more things for you guys to fill in. We have handouts for those of you who are joining us. They're on the tables, down, top and bottom, left and right. And they are posted on Carmen for those of you guys who do it with your fingers. All right? So a phenomenon is random. And pretty much random phenomena, like I said before, becomes regularly distributed after a large number of repetitions. So I might make 4 free throws in a row, but when I shoot 400, I'll probably still make about 70, 80% of them. I won't make 100% of them. And the probability of any outcome of a random phenomenon is the proportion of times it occurs. So random and probability are your two kind of, no, so let's go back one. What would happen in the long run? Okay, let's go ahead and fill this in real quick. Okay, so that's kind of like answering a question. The more people I sample, the more likely my data set is going to behave the way it's supposed to. That's the gist of this response. And here's an example from, I guess, basketball. Okay, and this is just my free throw percentage, 80% in the backyard, 70% when there's a referee and all that kind of stuff. But in general, the more free throws you take, the more people you sample, things should behave the way they're supposed to. So that's the gist there. Next one, you have random and probability. Kind of fill those in that little box on the first page. And I try to highlight the fact that these behave the way they're supposed to in a very large number of repetitions, so over time. Also, I did check on the heat. The word on the street is that we have some outside company that's working on something downstairs here, and they can't fix it. So be prepared to take your coat off as soon as you come in to class here forward. All right, we're going on to page 2, and then of course the notes are on the edges, top and bottom. More definitions. So, here we go. Definitions. So, let's see here. The sample space is a set of all possible outcomes. And an event could be a set of those outcomes, not necessarily all of them. And then the probability model has 2 components. All right, so that's pretty much it's pretty big right here. So you kind of distill through, okay, what's what, how can you read what's going on. We're going to use this notation going forward, like P of A. That's the chance of event A occurring. That's P of A. Probability model. Pretty much in the probability model, you have 2 components. You have the sample space, and then the probabilities for each one. The sample space is the list of all possible outcomes. And then the probabilities are, of course, the chances for each outcome to occur. So for your data from today, let's see here. The probability model from our in-class example would be gender of people in your row. And the sample space will be male and female. Those are only two options, okay? And in my case, we had 5/8 female, which means we had 3/8 male. and you say 0.375 here and 0.625 there. That's just for my example. Now, each of you may have something different. You may have had 100% female, 0% male, whatever the case is. But that's an example of a so-called probability model. Everybody that's involved and the chances for each of them to occur. Moving and grooving. All right. So here's a familiar example. Matter of fact, it might be very familiar to you. Wink, wink, nudge, nudge, right? Okay, so you've seen this last week. You may have seen this last night, right? You may have forgotten about last night because you're like, I'm tired of that class. That's okay. So let's see here. Here in this example, you have a couple's status, whether they're together or not, okay? Or happily married or whatever. And then, of course, whether the wife's parents were divorced or not. So you have four different types of people. This group, married, parents aren't divorced. This group, married, but your parents were divorced. This group, you're separated, but your parents not divorced, and likewise. So those are the four different people, four different categories in the sample space. An event could be a subset of the sample space. So couple status, well, we got two options here. You're either married or you are separated in this case. Those are the two different outcomes, if you will. Now, what's different from chapter 10 compared to chapter 6 is that we're not just going to be comfortable with the percentage of people who have some trait or not. We're going to discuss it in terms of probability theory. So the percent of married is 1384 out of 1498. That is 0.924. And yes, you'll need a calculator at some point today. Yep, 0.924. The separated group is obviously going to be, 076. Or it's 114 out of 1498. So there you go. Here are my outcomes. Here's the chance for each. They add to 100%. Everybody's happy. You have a probability model. And there, yeah, there's my little comment that we'll transition away from proportions to probabilities. All right. More movement. Here we go. So we have types of probability models. We have discrete probability models and continuous probability models. So in discrete probability models, we have countable outcomes. And when they're countable outcomes, they can assume finite values or fixed values. Another example could be like number of bees in a hive. Or how about this? In nature. How about that? That's even more obtuse. Well, we know there could be 0 bees. There could be 1, 2, and it could keep on going. So a countably infinite number of bees could exist out there, right? Just infinity, right? So that's an example there of that. Still discrete, but not having an upper bound. Okay, let's go to the next page. Those of you who were here earlier kind of saw a little bit of a sneak peek on this. All right, so there he is. Let's see here. Now, another example of a discrete random variable could be this. We're going to go ahead and track this. We'll say yeah here, and we'll say true there. Let's see what happens. guess I went backwards. Let's see here. We're not going to do some of these other songs. Oh, they want to log me out. Now you gotta count, right? Okay. All right, let me skip one part here real quick. Sorry. All right, well, here now you gotta count now. All right, we just gotta hear the bad part. Sorry, you guys. All right, enough of that. Don't tell me what you're gonna do later on and all that kind of stuff. All right, so what's my point? Well, he has some crazy clothes on. Yes, he does, right? But it's a discrete random variable because we can count the number of times he says his name and whatever else he does, okay? So that's a discrete random variable in the making. The other hand, there are things called continuous probability models, okay? And so how is the length of a song by anybody, 2 Chainz, Nelly, whoever, Michael Jackson, Paul McCartney, how is the length of a song continuous and not discrete? Why is that continuous? Yeah?
Because it's time and you can never measure time to like a certain...
To the exact. Right, so it's a measurement. And it's probably going to be a fraction in some kind of capacity. Okay? And for the most part, we can say it's going to not be an integer, right? If we try to measure his songs in minutes, they're not exactly 4 minutes or 5 minutes. And you look at your own playlist, you'll see so many minutes and so many seconds. So let's see if this works. Okay, so here, I guess some of his favorite hits. I don't know what he has. Okay, birthday song. We will not play that today. But it's kind of entertaining. So I guess the point is, let's see. Yeah, there you go. None of them are exactly 5 minutes or 3 minutes or 4 minutes or 2 minutes. They're always kind of like including a fraction as well. So you're right, they're going to be continuous in that case. Maybe at the end of class we'll play. No, maybe we won't. All right, let's see. Let's make sure we're still recording because that's always tricky. Okay, yeah, we're still good. All right, so let's go here. Okay, disappear. All right, so there we go. So then you can use probability models and density curves to find probabilities for those. That's no problem. Remember, the whole area under the curve is still 100%. Okay, it's still going. I heard something chime, so it kind of threw me off. All right, so there's that. Let's see here. Yes, the continuous probability model assigns probabilities to the areas under the curve, and it can assume any value on that range. From a long time ago, we had an example like this. Okay, I think it was in chapter 3. So the heights or the temperatures in Columbus are 35 to 40 usually, and so we want to find probabilities, of course, corresponding to that. We haven't hit 35 in a long time for a high temperature, but that's okay. Now, what percent of the time is the high temperature below 38? Well, what you would do is say, okay, and again, temperature is a measurement, right? So it's going to be, it could be 37.6 degrees, it could be 37.8 degrees, but the weatherman will probably just say 38 degrees. So the probability here is 38 minus 35 out of 40 minus 35, which is basically 60%. So according to this, if everything is behaving the way it's supposed to, there's a 60% chance that the high temperature is below 38. Now, one thing about continuous probability models is that we do not have area at one specific point, one specific outcome. We look at areas and regions. So technically, thank you, kind sir. How about that? Okay, 38 degrees. Okay. Yeah. So the whole point here is that in continuous random variables, the chance of being less than a number is equal to the chance of being less or equal to a number, because there's no area at a single point.
It would approach zero, right? It'd be like 1 over infinity.
And then you keep going down, down, down to zero.
Yeah.
So
1 over infinity is basically zero.
the limit of 1 over n as n goes to infinity, 0. Let's see here. Yeah, that's enough for that. Okay, random variables again. We're going to go ahead and keep going. The fun part of this chapter, these 2 chapters, is kind of coming up. So just hang on your seats. No more music videos. How about that? For you guys over on that side. All right, so let's see here. A random variable is a variable whose value is a numerical outcome. That's fine. And then, of course, we have a probability distribution. It's kind of like a probability model. We just use variables like x. Okay, so then, what if it's the number of times a student comes to class on time, where it could be 0, 1, 2, 3, 4, 5, etc., and you keep having a probability associated with each one of those. Next group. Let's see here. So chapter 10, I'm just flying through that because we talked about it already in recitation. Talked about it last week. Talked about it in chapter 6 in some kind of ways. So just kind of adding some meat to the bones. Subjective probability, that's kind of like my way of saying, I think the Buckeyes are going to win tonight. You never know. Right? Okay. Did I calculate? Did I scheme and plot? No. Just a personal probability. 80% chance. Let's see here. You guys should know this. Probability for each outcome is always between 0 and 1. You've been doing that since your middle school, probably. and all the probabilities basically add to 100%. So you didn't forget anybody, you didn't add anyone twice. And again, final commercial, we have extra copies down here on each of the tables and up top on each of the tables. So in case you need those. And they're posted on Carmen as well. This word was in your recitation, disjoint. Okay, it is not like a cousin of the word dysfunctional, but two events have no events in common, or they cannot occur at the same time. It cannot be both Saturday and Sunday at the same time. So they are disjoint events. You cannot be both here in class and physically in your room. Mentally, I don't know. Physically, you're here. So when you have disjoint events, you just add them up, right? Check this out. In my example, the chance, say Baker's, I say earlier example, the chance of being married in the earlier example was 0.924. For the purposes of that study, you couldn't be both married, living together, and separated. If you're separated, there's a whole different, you have to not be living together. So the chance of being separated is 0.076. So to follow this rule, what percent of folks are married or separated? Well, that's everybody in this study. It's not always the case that you add these probabilities are equal to 100% unless they cover the entire sample space. The complement rule is just it's not the opposite, but you can think of it like the opposite, okay? So if there's some event A, right here, then the chance A does not occur is just 1 minus A. So here we have some event M. So the chance of being married is 0.924. Well, then not married is just 1 minus that. And then you get the idea. Not married and separated are the same thing. So you guys know that. That's kind of intuitive. Now get into some good stuff. We'll probably get to a little bit of chapter 12, maybe not get to the whole thing, but we'll definitely finish up this week, and then we'll do 11 as well later on Thursday. So Venn diagrams are pretty cool because they're kind of graphical displays of probabilities. And so here, I think I included the Venn diagram in your notes. So if you have 1,000 folks, and you could write this as a table, but we'll hold off on that. Let's see here. Okay, there's that. It says here 47.5% were female, 42.5% were female and right-handed. So it is possible that they're right-handed female, so that those sets will overlap. And I like to kind of do some little arrow or whatever. There. Okay, then now we have this whole set. Ooh, let's get some colors out. That's great. So blue will correspond to being right-handed. Well, you have 88.7% people who are right-handed. How fun I got it on the left side, but that's okay. If 42.5% are female and right-handed, then you kind of think that maybe, just maybe, 0.462 are those men that are right-handed. And then you add those two groups together, that's everybody who's right-handed, guys and girls. So I'm just kind of taking that 88.7% and breaking it down or subdividing it into two groups. 0.425 that are women, 0.462 that are men. And that's how I get my 0.887. On the other hand, 47.5% are female. So let's go female. Let's get a different color. How about green? There. So 42.5% are female. I'm sorry, 47.5% are female. And right-handed. Right-handed is 0.425, which means left-handed is 0.05. Okay, there we go. So the 0.425, the whole set are all the females or women. 47.5% are female, and then you can divide that. That's 42.5% are women that are right-handed, 5% are women that are left-handed. This is a little bit wild, but it's a little sidebar, I guess you could. Oh, I'll hold off on the sidebar. But this could be represented as a two-way table if you think about it. You have gender on one side, and then your dominant hand on the other side. But this is not everybody, because what if you're a guy and you're left-handed? Well, that's going to be 0.063, I guess you could say. Remember, the whole area adds to 100%. So if these numbers here, 0.462 plus 0.425 plus 0.050, is 0.937. Well, we got the right-handed women, we got the left-handed women, got the right-handed guys. Oh, we forgot people like me, left-handed guys. Okay. So this group here will be the left-handed women. This group is the right-handed women. This will be the right-handed men. And these guys are left-handed men. Okay, so sleep on this for a second while magic hopefully appears. rounding error. Oh, 462. There, that's right. Okay, now again, your job is not to know all this right now. Your job is to let this all just marinate, sink in, okay? You can use a Venn diagram to represent the situation, or if it helps you, you can look at it as a two-way table.
I don't think a Venn diagram really suits the situation very well. None of the situations overlap. Like, you're either a man or a woman, or you're either right-handed or left-handed. But like, I don't know, like the center area, the .425. Like, I've done Venn diagrams before.
Yeah.
And that was usually the area that like both sides had in common. But you have right-handed males on one side and left-handed women on the other. You can't be a man and a woman, right and left-handed in the middle.
Okay, right. So we're not talking about, we're talking about,
What's the point of it overlapping in the middle? They're separate categories. Why are they in the same thing?
I guess we're looking at, maybe a two-way table is better than,
Yeah.
yeah.
Like, I think it suits the other, like the marriage situation.
Right.
You have like
The
women
parents
that
or
are
whatever.
separated, women that are divorced, and then like the ones that have like their parents divorced or something like that in the middle. Just they would have some common.
Well, you're going to see more of these in your homework and the quizzes and that sort of thing. So, I guess the issue is we have two variables that we're looking at as opposed to one variable with two different situations. So indulge me, if you will. All right. Now the fun part. Calculate the probability that a rounded selected person is right-handed, dominant, or female. Okay, I can handle that. You have a little picture in front of you. And I'm just going to put the numbers in. So according to this chart, the probability of being right-handed or female is equal to just the sum of all the partitions. I think it's a 0.937. That's one way of doing it. Now, be prepared for this approach. The chance for being right-handed was 88.7%. The chance for being a woman was 0.475. So right-handed, or female is going to be like 887 plus 0.475 1.362. What was grossly done incorrectly? What did I miss?
You added the part in between hours.
Yep. Okay, so the whole point was we had this overlap here. So we got to take it out once. $937 again. So no matter how you slice it, you can draw a partitioned Venn diagram, or you can kind of use the formula outright. Or if you want to be daring and exciting, you go back to your old days, right? You just say, okay, fine. Right-handed, well, this group. Boop, boop. Women is this group. Boop. Add up the purple check marks, that's your answer, 0.937. And that's the organization issue we talked about earlier. So add up all the purples, you get 0.937. Or you just do them right here. Same group. So we're going to transition back now into the mathematical side of this course. None of that stratified, how do you feel about double blind, non-response, those kind of things. Categorical, qualitative. Okay, that's all laying the foundation. Now we're getting our calculators out again. And formulas. Okay, so we just use the so-called general rule of addition, or the so-called general addition rule. So for two events, A or B, you just add them up. But watch out for subtracting any kind of overlap. So I like to call it, you take the sum minus any overlap. There's no overlap, big old goose egg, nothing to take out. Oh, that's what I heard. The next question says, where do we see this before? We saw it before in chapter 6. And I think you may have seen it last night. Yes? Maybe not. Okay, so it did show up before where I said something like event X or Y, and you had some table. And you have to find those probabilities or those percentages. Moving forward. Well, if there's no overlap, then what do? The events are called disjoint. So what is probability of A or B when they're disjoint? Well, you still have the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. But if they're disjoint, this guy is a big old 0. So when they're disjoint, you just add up the probabilities. Very simple. No subtraction, none of that stuff. If someone's left-handed or right-handed, or I'm sorry, their dominant hand, right? You can be ambidextrous, I guess, but you should still have a dominant hand. Next one, okay. It says here, calculate the chance or the probability that a randomly selected person is neither right-handed dominant nor female. Who am I talking about? Neither right-handed dominant nor female. Right-handed dominant or female is all the purple. Who's left over? The men that are left-handed. I'll use a different color. Let's go blue. Okay. So the chance for neither right nor female is actually 1 minus the chance that you are either right-handed or female. So now, those of you who are into linguistics or English, either or, the opposite, I guess you could say the true opposite is neither nor. And so that's just another application of the complement rule. So yes, I don't know if I give you these rules on the midterm. I think you'll be able to figure them out. No, we got some more that are more difficult. Moving and grooving. It said to calculate the chance that a randomly selected female is right-handed dominant. Okay, let's put on our chapter 6 thinking caps. So with that in mind, we had this chart. In chapter 6 world. And let me know if I did anything wrong, incorrectly, before we go down too far. This is left-handed. This is right-handed. This, I believe, was female. This was male. Okay. Putting on our chapter 6 hats and thinking about these in terms of percentages of probabilities. What do we know about this person? Is this person female, male, right-handed, left-handed? What do we know for sure? Female, right? If we know that it says there's a calculated chance that a random selected female. So if I know someone's female, no offense, but I don't really care about the guys. The female percent was 0.475. If I know she's female, how likely is she that she's right-handed? Is it better than 50% or less than 50%? Better than 50%, right? In fact, you can find the ratio. So out of the 0.475, there's a 0.425 chance that she's right-handed. Now, in chapter 6, these are all integers. 5, 43, 46, 6, and so forth. In chapter 10 and 12, we have decimals to contend with. But the same ideas tend to work. $89.5%. Let's see here. All right, so we know that the woman, so we're saying here 0.8947. If I know she's female, the chance of being right-handed, that's our little tricky new notation here. Whoa, there's like a division symbol in there. There's something crazy going on. The known event goes behind the slash, being female in this case. Notice also how the known event goes underneath the division symbol. It's the denominator. So who are we talking about? The known event is always like our, in terms of some group. In terms of means it's like our denominator, our name group. Okay? Then the other group is this guy. Here's our marginal total, 0.475. But we saw this back in chapter 6. These different cells are intersections. L and F, L and M, R and F, R and M. So we have R and F, my numerator, out of F. A long, drawn-out way of just getting this answer. So I'll make a little note for you. Review this.
R and F need the point 475 though.
Let's see here. So 0.475. R and F has to be. So we let's see. We use that word and.
Oh yeah. Okay.
It's got to be where they intersect.
Okay.
And then there's my little notes. The slash symbol is like the given, okay? And everything behind that is the conditioning event. And we keep on going, that's fine. B, given that A occurs. Right, got it. And then here's the formula. I guess you can write that down. Notice how the event that's behind the slash ends up in the denominator because that's what we're talking about, out of that group. If I know someone's male, boom, it's out of these guys who are in our sample. And then the two events together, maybe you guys have seen this before. Uh-oh, right? Seen that, right? So then this symbol is like this. If you ever seen that kind of upside down U, then that's what it's talking about, the intersection. B and A together is the same thing as A and B together. And just to make sure all the math works out, this cannot be 0 in the denominator. You can't divide by 0.
If you get more than one, you negative it all.
That's right. That's right. Let's see here. Yeah, we'll be okay. All right, so let's see here. Watch out for the wording for conditional probabilities. Okay. So things like, calculate the probability that a selected female is right-handed is different than asking calculate the probability that a selected right-handed person is female. So just things like probability of R given F is not the same thing as a chance of F given R. Just watch out for the wording there. Moving, forward. I guess we'll get through. Well, we're not going to stop. Well, this will be our last one. All right, so, and we'll start right at a las ocho on Thursday, okay? So, this one here. A.C. Nielsen finds that 81% of households have computers. Okay, nice. The chance of having a computer is 0.81. That number is probably a little bit higher nowadays. Of those 81%, so I'm going to say if I know someone has a computer, the chance of having internet access is 0.92. What I like to do is kind of read these problems and take notes along the way. Otherwise, you kind of get too confused sometimes. So if I know someone has a computer, the chance of having internet is 92%. What's the chance that a household has computer and internet access? How do we figure this out? It's a sequence of events.
Multiplying.
Multiplying. Yep.
It's 92% of the 81%.
Exactly. So we want to go ahead and take them, go ahead and multiply. So the first thing you got to do to be in consideration is say, okay, there's an 81% chance of having a computer. Of means multiply in some cases. 92% of them have internet access. Now we're good. We'll go ahead and that's 0.7 452. Okay, that's where we get that from. Now, here's where the voodoo comes in. This guy is a probability of C. This guy is a probability of C. I given C. And then we're asking for the chance of C and I. So in voodoo, you have a new formula that comes out of this. Okay, the general multiplication rule is birthed out of this voodoo, I guess you can say. Now, if you know the answer right away, you don't necessarily need to go through step by step and put down the different set theory. Just showing you what you multiply to get the answer. But the general multiplication rule is what we just did. If you want to find both events, take your marginal probability and multiply that by the conditional. I'll leave this up there for those of you guys to jot this down, and then we'll pick up right here on Thursday. I guess the bottom of page 6. Hey.
I'm Jasmine. Everyone keeps emailing you.
Wait,
About the exam. Said I had
you
one.
can't take it?
Oh, there's one tonight, right? At 4?
Yeah, you coming?
Mm-hmm.
Oh, University Hall 0082.
Okay. Thank you.
All right.